How are you? Monday morning? Yeah, I realized last Friday we went on and on. I kept talking, so we'll try to make it a little bit more interactive today, let you ask questions. I don't have too much material. We're really going to be focusing on how people do lean design and manufacturing. You have to learn fast. You focus on the minimum that you need to take yourself to the next step. If you start thinking too much long term, you get distracted. It is a challenge, especially when you work as a group. You'll always have a dreamer, somebody that wants to talk about, 3-4 steps down the road. And a lot of times, it's not useful. It is useful to have a vision, a general vision of where you're going, but you don't want to paint that future in details because you don't know it. And it's a very common mistake with young engineers, trying to really visualize the future when in reality you got 3 or 4 steps before you get there that you don't know. When I present the case study of this little machine, what I'm going to do is show you the first patent. There is a whole 12-hour module on law and technology, essentially patent protection for when you go ahead and invent something. It does come handy when you are actually commercial, so it's a very long-term investment. The other outcome is you do force that general thinking that sometimes on the day-to-day you don't do. What are you trying to achieve? What really is the usefulness here? Because that's what you try to capture with a patent, what you are after, as opposed to one very specific idea that you had in mind. Because at the end of the day, you'll have a number of ideas, and you have to prioritize them, because your patent attorney may like them all. so that's always a challenge. One more thing about patent, because I want to speak a little bit more generally, is there are things that, of course, you can protect. There are things that are probably not worth, but it's worth including them in the application because you publicly disclosing those concepts, and nobody else can come and say that they invented it after you disclosed it. So on something that's been publicly disclosed, you can't file a patent for it. So that's always a key limitation. If you have an idea, you can't go and present at a conference and then file a provisional patent application. Now, I use the word provisional because the first thing you need to do is essentially a filing that never gets published. It describes what's the intent of what you've invented, and then from there you can you have a year to convert that application. Otherwise, you lose it. So it's a little tricky. 1 year sounds like a lot of time, but when you actually get to work, it goes by real quick. And then you probably wonder about that orange thing. That's a prototype for something completely different. And I'll describe that to try to emphasize the value of having a physical object with you for your understanding when you try to build or analyze something from an engineering standpoint. Have you all seen the Friday lecture? At least 2/3 of you were here, right? Who's new? Okay, good morning. So this is a continuing module. It's a startup in technology, and I emphasize through over time the value of the customer, but today we'll pretty much assume that they're there. So the general process of bringing something to market is commercialization. So again, we assume now that we do have a customer. We're a very small group of people, very smart, and then we're trying to get into a lot of application, a lot of use of our tools for typically business applications here is what we're after. I wanted to emphasize the value of thinking strategically about how to go about applying your application. And this is probably, I emphasize that in lecture 8. But I'm bringing it back here because my story, or the story of our team for MMT, that tester, may or may not apply to what you would be considered doing or what you'll see other people do. So I wanted to provide a little bit that general context where you can start early on into technology development with a joint venture. So you'll partner with either a larger organization or another small, mid-sized organization that has complementary skills. You can also already identify, if you see that there's many applications. I'm looking at the lower right here, essentially licensing ahead your technology. My impression is it all depends on how many applications you can foresee. That's the x-axis here, and how much money you need. So this chart comes with a lot of explanation. There's a webinar from Don Breaker going over all the details of different cases. So for the HSD tester, the bootstrap model is what we utilize. The reason there's few applications for the initial market is this tool is for measuring yield strength, and a lot of times on a new construction, you know the strength. There's a minimum required that you have to follow. So for our initial market, we had to find people that didn't have that information. The bridges, they have really good records. It's filed with the state, and the state normally doesn't go bankrupt or gets acquired like a lot of those companies do. For buildings, it's not as critical. So if you have an existing building, they can cut a little core sample, a little round piece, send it to the lab and get the data. It's hundreds of dollars. It's really not worth going after with something completely new for technology. In aerospace, it's the same story. They really control. The strength is one of the very basic things they verify. They verify a lot more properties. So there's two kind of initial application. One is pipeline. The other one is when they do repairs. So all Department of Defense right now, they are considering adding on, spraying metal on metal to remake for corrosion loss or wear. And there's a sense there of really getting the material property, including how much ductility there is in the coating. Some of those coatings can be fairly brittle. The challenge for us there is they're still trying to get their process certified with the most sophisticated tool out there. So it takes time, and it's a very small market as we speak. Then on the so few application, then on the amount of money required, I think the chart fits about right. We did have to build hardware, software, and develop our customer, but we didn't have to start a plant or anything really big. So it's been mostly time and expenses. So our human capital has probably consumed 80% of our total spent over the years. So the reason to be very careful, and I emphasize that many times, but I decided to bring back that one slide. I always go through previous lectures and try to make sure I've got it right. If in our case, the operators, the pipeline operators have been used to operate without having the information. the day they have the information, there's tremendous implication, and we already talked about that in the last lecture. And this is a chart provided by one of the early adopters of our technology, saying you need a vision, you need the skills, you need an incentive, you have resources, and a plan. These are 5 ingredients that you need if you're going to actually make something happen. So when I was saying it takes multiple years, I tried to put a little more flavor into this. Essentially saying that every time that you meet something, people are either confused, anxious, they're going to resist, they're going to be frustrated, or they won't really, they'll be ready to go, but they won't do it right. And then after that, it takes time, some time to pick it back up. So if somebody tries something and didn't really work for them, we have that in 2 cases right now, and it just takes even more time at this point because they've kind of got their feet wet and they got burned, and now they're gonna wait. Okay, so prototyping. You don't know a lot of things. You don't know really how much it's gonna cost, how you're gonna do it, and whether it's gonna work the first time. Well, you should assume it's not gonna work the first time. That would be a really good, fair assumption. The process here is there's stuff you don't know, and there's possible outcome. And it's been ingrained in our team structure that by the time you've identified 2 or 3 really key unknown, stop there. Try to get some answers for those things, especially if they matter a lot. In our case, it really was making it portable. That was our first thing that we knew we needed to do. We had no idea how we were going to do it, so we just started right there and iterated. The first few times we probably had 3-4 months between the prototypes. That was really, really fast. So if you think about designing it, building it, trying it out, and starting over again. But that's how we got a portable tool pretty quickly as well. And I'll go through the details there. But the general concept is you brainstorm quickly, you identify what you're going to build, then you build it. And you don't hesitate. When you're in building mode, you don't want it to be like, oh, let's stop. We could have got this other thing. Because if you start thinking about it in that mindset that there's only so much time in your thinking process that is valuable, and then you could move on to the next step. So if you see your friends or a small company that, let's say you hire or anybody else, or you're the master, you're the one to make this happen, the way it works is you have to accept what we call the failures. So if people are afraid that they'll be blamed if they do something wrong, all of this goes away. So these little 3 yellow dots don't get picked because nobody wants to own them and say that they haven't considered the others. So the couple slides before, both from this fellow here that was doing hardware development as well, and they made some statistics. So if you try 20 things, you got a 60% chance of success, and when you're 50, you're at 90. So ultimately, you really want to succeed, right? You don't want to be a 50% chance of success, which means you have to try a lot. You have to go and try and try. I mean, it's one thing I really want you guys to remember is don't try to do it all at once. It looks nice, and again, especially as a young engineer, you have it on SolidWorks, and you're like, well, maybe this thing is going to be too heavy there, and should move. Don't worry about it. You want it to work, and one of our prototypes, we had to hang these dumbbell weight to the back of it because we got our center of gravity wrong, but it didn't matter. We knew the next time around we're going to be able to fix that. Our customers saw it. We didn't even know the time we flew for the job. So we got there in the hotel room, tried to run this thing, and it tips forward. So went to the hardware store and bought some weight, just hang them. So it looks, and we had also this thing looked like an airplane. It was about twice this size with all these springs. And I was almost, I'm not a very shameful guy, but when you got the big shot at the oil and gas company sitting beside me and say, yeah, I know it looks like an airplane, this one, but we're trying to get it to work. We're trying to get some form of reproducibility was what we were looking for back then. Not accuracy, just reproducibility. So we kept trying, and we talk about try 50 things. At our status for what you're looking at here, I would say it's closer to 100 things we've tried. And thankfully, the design team is still there because not all of that is documented. So somebody new comes in and they start talking about something, so well, we've tried that. And this is one of the problems. So there's a lot of value in thinking that way in that design process. Okay, let's get into it. So this is the one slide I presented last time about the history going from 2015 to today. And I'll give you a little bit of a benefit here, which is I will explain how it works today. I hesitated, but I decided we don't have tons of time, so you guys don't have 1,000 man-hour to think about this. So we'll just be acknowledging that and moving forward. So where the four little arrows are the four grooves that are made by the tester. So it starts right here. There's four of them, and they move this way. This, and this are what we call the leg of the tripods. They are the reference point to make sure that everything stays perpendicular. It's also touching the pipe or the surface that we're testing. So the four grooves are all made at the same time, and then you can see a little bit the zigzagging. That's our contact profilometer tool that goes behind and measures the width. So you can see it in action, hopefully. And it's accelerated. But that entire thing is what you see. It's what you see moving there. Slightly different, but. And what's behind these things are our contact profilometer. We got two of them. That's it. You want to do it again?
No, I mean, is it accelerated?
Oh yeah, the test takes about 10 minutes.
Okay.
But it's
Because it's really fast.
yeah. So these things and underneath of it, I'll show where the tree floats are here, and then the four styluses are all lined up in this model. Didn't used to be the case. Okay, so how does it work? Again, today from an analysis standpoint, I mentioned about four stylus shapes. So the first process is to run a bunch of finite element analysis on these three different shapes for 100 different combination of yield strength and work hardening. When I explain that to our customer, most of the time I see some, I don't know what you're talking about. But here it seems like it's registering. It was my thesis work to show that there's a unique relationship between that response and the tensile property. The biggest difference for my thesis was using only one stylus. It was a cone, and I was keeping track of a lot of stuff, including the depth and how much the material was piling on each side as opposed to the reference depth. And the way, even at the beginning with the customer, I was explaining that if you try to plow wet snow, it's different than just a flurry. So the flurry is going to go and pile, whereas the wet snow is going to consolidate and not go as high. So So the concept here of getting the work hardening in the 3 or 4 first version of our unit was going to be very, very difficult to reach accuracy. It was possible in principle, but we were within about 20-25%, which is not very useful. But just to emphasize that, we stayed with one stylus for over a year, just producing results and starting to analyze it and working more by direct comparison. So we knew one steel was this kind. We were comparing to another one that was almost the same. And we were spending a lot of time handling the data. But at that point, we were focusing on just the control, just getting our equipment to stick to the surface, really was the goal. It was about a year. Okay, so I mentioned here starting in 2015, but the first provisional patent was filed back in May of 2013. And you can see it here. It was really the concept of having floats, I think we were calling them, with the testing head in the center, so it will adjust and follow your surface. Some of the challenges back then were really not knowing what we were going to test. So the size was a concern. People were thinking, let's go and test some welds, because welds are known to have very variable properties, and even if you have really good record for the material you purchase, you still don't know your steel quality. So the very first prototype we built, the idea was to make the distance between those float just about this much. We had a few pieces made by laser sintering, very complex, and what we realized is the issue wasn't so much with making the core, but all the instrumentation that had to come with it to be accurate. So we could make the device, and we may still make it one day, but we spent tremendous amount of time thinking small. And I think I want to show you some of the craziness back then. I'll post it just because it's very abstract when you haven't really seen and driven into any of those. So this is the utility, the granted application. It starts with some very, very basic concepts. So here we already had a third leg, but it was behind. Then we just go on and start having a little bit of a beam here to hold the central leg. So this is only showing half of it, so it wouldn't just collapse. That we worked on that for a while. Then we started to look into more load applicators, starting to think about how this whole thing is going to move. Then there's always a question, how are we going to measure the profile? And we thought we needed the height, we thought we needed the depth, so we were kind of, oh, this was very nice. So looking into a tool that would follow and trail and touch the surface and make all sorts of measurements, different versions of it. And I think near the end is where we thought we were really getting, yeah, how we were going to do the surface preparation. Here. So this was, even as of today, pretty thought through, because in this one you do have the floats that are making sure that you completely touch. And then you have something here that is your loading configuration. And there was a possibility of this one here being on a swivel. It's because if you take a chair on a curved surface, it doesn't touch. It could bounce back and forth. So the idea was to have this on a swivel. But the honesty there is, we still had in mind we could go by with one stylus. So we didn't have at that time one point right dead center. When we moved to that, everything got a lot easier. So what we did is we put one right here, and then we put 2 grooves on one side, 2 grooves on the other, so they don't interfere with each other when you travel. So a lot of learning when we got to that point. Yeah, the idea of preparing the surface never made it through, but that was, again, a waste of time. We should have continued focusing on the one thing we knew we needed to do. Questions so far? What do you guys think? Are we making? Yes?
This is kind of a question about the very initial stage when you were trying to design this.
Yep.
So did you identify one particular problem? Because it seems like the device does like a number of things, and start prototyping on that one thing, or did you start the integration right away?
Okay, the question is about doing one thing at a time versus integrating. We had a certain level of integration because we wanted to run tests, go to conferences, write papers. So that's the minimum viable concept. So you don't take just one piece and keep working on that, because your road test is the valuable aspect. So we needed to be able to go on the road. And that's why it's a very good question. So this one model here, you see the brackets, you get a sense for how simple the drive system is. The electronics are on the table right next to it. Very, very simple, connected together. So the one thing we were working on, and you can see it here as a relatively smaller version, was that core. That core used to be only a little square this high with one stylus in it. And because we were testing pipes, we realized early on we can increase the spacing between those little floats and not run into any issue. So we gave up very early on, it was in 2015, trying to make our device compact. We just broadened the span. And when I was talking about accuracy, you can see it here in 2015. We've got 3 springs, so 3 styluses. We went from 1 to 2 and still didn't work, so we moved to 3 very, very quickly. And that was a last minute thought, so that's why it did go behind as opposed to lighting them all up. So we were okay with that. So the idea there was really just building on what was existing to get to the next iteration. To be able to, so when you have a platform, when you have something that works, we were drilling holes, changing one part at the time and trying something else right away. So there was, yes?
So, I'm sorry to cut you off.
No.
What was the composition of your team at the time? Can you describe like
Yep.
a rich mechanical testing problem?
Yes.
Or was it like a precision machine design problem?
So the question is, what was the size of the team? And then the comment was, it looks like a precision machine design. So we had a senior mechanical engineer that had just general prototyping experience, nothing in precision machining. We had typically half of a co-op. So we had a co-op student that was spread between the consulting company and the startup company. And then a few more senior people with general experience in material science and all that. When it came to the joints and some of them, what is really precision machine, we were visiting with experts and sitting with them and getting some insight onto things to do. In hindsight, we could have gone to a consultant a little earlier and used them a little bit more. So we had some catch up on that right after we did our 2016 prototype. We realized at that point that we had still a lot of limitations. So we brought somebody from the outside that has done a lot of precision machine and taken that loading mechanism, essentially not so an outside consultant, our experience was not helpful with this. We tried. We had a bunch of people come in and they're starting to look at it and saying, well, maybe I could help you with finding a machinist or something like that. But because there's a lot of long-term thinking, it's just all new. There may have been a few people back then that we know now that could help us at that stage. But the place where we got some tremendous payback right away is hiring somebody to take this and move it on the pipe. So that consultant brought in, it wasn't hydraulic, it was an air piston system. They had a lot more span for moving onto the surface. So we probably had spent a year trying to control this with springs and having trouble at taking off. So when I was talking about the dumbbell, but when we were doing that, because we own all the hardware, when we needed to make a change, we were able to do it so quickly. So that's the expense. If you hire a consultant and they take on something, and now they need it machined, because we were doing a lot of our own cutting and machining, so that was just speeding up everything. Because when I say a design cycle of 4 months, the trial period is 2. So you got 2 months to think about what you're doing next and actually building it. So it was very, very short and driven by some of our research contracts. So the entire NSF phase 1 you have to complete in 6 months. And if you're gonna make it right, you need 3 shots. So, and you don't talk about all of them in your report. You can, but it's really, that was a key to our success. So I'm sure if we had started with more money and being able to take more time early on, we could have gotten more outside expert to help us earlier on. And that's something we're doing a little differently right now with our second baby. We are taking more outside people to help us. So I have already mentioned it. So when we moved into our second phase of SBIR is where we had a significant budget for a design consultant. And the little white here is an air tank. It's still on our unit today. And that's what's loading the entire core. It's got only two contact points. Load it, and you can do any diameter and things like that. Just before that, we were still, because we have our frame. You see the frame here? So that gets strapped on the pipe, and we still use strap. We haven't gotten to these roller chains and things like that. So we use ratchet straps, put that on. I'm sorry. This is frustrating. Put that on, and it used to be the movement of the core. It will hit the pipe, load the spring, and run the test. So there wasn't any drive system. It was just, you go. And we were getting valid tests. So we would first move into our loaded configuration, then activate the other styluses, put everything in place, run, take everything out. Again, the beauty of that is we wanted to change, took the core out, put a new one in, run again, wearing styluses, all sorts of stuff that was very common back then, were things we were working on. Again, and you can see here back in 2016, we had put magnets on our device. Was creating tremendous trouble in attaching it reliably at a specific height. We had all sorts of adjustments to make sure the thing will work properly. But then we were going to a customer warehouse and they would time us. They had how long it would take to run the test, because ultimately that was one criteria for the early on. Say, you're not going to spend a week there testing my pipe. I'm not going to let you do that. So it's got to be quick. So we were mostly judged by how quick the process was early on. So we took those off, this year, 3 years later, we are going to be adding some magnets back into the system to test big tanks, not to test the pipes, but so kind of new application. Did we struggle with them too long? Probably not. It was maybe 6 months that we were trying to work it out. We had noise in this electric noise, so we were running on batteries at some point, 12-volt batteries, and that was working fine. So there's all sorts of pieces that are trouble, and you find a temporary solution that allows you to move forward. So yeah, I remember we did some paid trials where you fly, you go and buy some batteries, and we only used it a day, so we would sometime return it to the store. It'd be okay with it. That's just, you explain, it's like we're a small company, we need this for the day. Yes?
So you said you're using the magnets again. So I'm assuming that some of the things that you tried in 2016 is useful now. How did you maintain documentation?
Yeah, so the question was about the magnet from 16 to now, how the documentation is helpful today. I think the quick answer is when you have pain, you tend to remember it. So we don't have to go back to what we wrote for the NSF back then as to why we spent that money and it didn't work. When I was talking about the adjustment, that was the biggest thing. So right now, we actually keeping our main contact point and we just add that on with a spring to make sure it's easy and it doesn't affect everything that we're doing right now. So there's only so much that you need to remember to be able to take it to the next step. And we expect we're going to do 2 or 3 iterations in the first 6 to 8 months, just adding something or hopefully taking something out that's not necessary. And well, we're putting it together in 2 weeks, the first one. So the earlier on you are, the shorter the cycle is what I recommend, because you'll learn very quickly. So some of the details of this now. And I hadn't spent tremendous time with it recently. We used to apply the load just like this using carriages or linear bearings. It was causing our height to be much higher because you needed a long carriage and then you had all the loading devices on top of it. It took us 2 years before we were at that level of refinement to even determine what was the friction in our linear devices, because you worry about that from day one. Like, I'm going to have friction here because I know I'm loading perpendicular to my bearing. But so what if we found because we found it was 3%. It causes some issues, but we still had so many other stuff to figure out that we're glad we didn't spend more time thinking about, how to reduce that. We wouldn't have a company. So at some point we needed accuracy. So the tool was working. We had figured out noise. We had figured out how many styluses we needed even. And we had paid work. And now we were going to go for a big blind test, essentially. So at that point, what we did is we put bearings, and the first bearings were put the other way around. And there was some theory behind an advantage of having it transverse, because then you really don't have friction in the direction that you're interested in the load. But this worked out a lot better from an instrumentation standpoint, because you got all of them next to each other as opposed to having 2 on one side and 2 on the other. So, and it's very, very stable because you're moving this way and your little beams are running that way. So in theory here, you have a double answer. So the friction in your bearing is going to contribute, now let me take that back. The friction from your test stylus with the surface, which we took a while to get to the point of determining, but it's about 20%. So 0.2 is the side load as opposed to the vertical load. So because you got these two loads here, when you're measuring the force on the other side, it's a convoluted answer. It's got the two factors because your contact point is below the bearing height. We decide to account for it. We decide to account for that as opposed to turning it the other way around because that 0.2 is very constant. And in numbers, it's 0.5%. So we don't know within 0.5% that's acceptable on load, essentially. So lots of trials and error on this one. The loading has been something we worked on probably 5 to 6 times before we accepted the best optimized compromise as of today, because the next thing probably is to start shrinking that back, integrating it, and all of that. But we know all the ins and outs of this process here. The other feature, these LVDTs that are behind it that go back and forth you saw in the video, they are still on carriages. And I was surprised to see that. So this is our legacy 4-year-old little carriages that are, those are insulated, so they protected against dust and even water. Sometimes there's a little water that goes on this. If it ain't broke, don't fix it, right? So it's not causing any issues. We control these styluses with a stepper motor. So it's very, very simple technology. It goes by increments, and we use those step size to figure out where the styluses are. So there is some redundant measurement that's being done, but it's not used for determination. Now, there's been times where before we got to get everything machined right, where we had too much friction and the stepper motor will stall sometimes. Ooh, data's off. But it gets to be so off that you know you have a problem. The other important thing to know about this assembly is every day you run on a flat plate to make sure that everything is working right. So you work on the known samples every day, and it's what you do with hardness testing anyway. So if something in all the system, whether it's the load or the displacement measurement, because these are the only two things we measure. So we apply a relatively constant load with those springs. They're activated by 2 motors here, so it's all automated at this point. This is our first version that applying the load is not with a wrench, just to be clear. We keep monitoring that load. It doesn't change much, but it'll be a couple % during the test, and we still need to know that, so we account for that. That's not super hard. So yeah, you apply the load with this, and then you measure the width by this thing back and forth. That's it. That's it. So back in 2017, we had changed our surface preparation procedure for this. And the new process was faster, but it was bringing a lot more contaminants into the surface. It did take us a month to figure out exactly what was going on. Brian, if you remember, you did some of the microscopy that summer, looking at what was on the surface, the size of the particles, and showing that they were just embedded. So we had the very first step, the big particles were getting stuck into the surface and then wearing our styluses. And we still couldn't go, the problem with our first surface preparation process, it was too long and you had a risk of not doing enough. So now we went to too much and we knew what was the problem after a month, and then we were able to finally engineer. So we talk about all these things that you figure out along the way. If you styluses wear, and we didn't have at that point a really good way to figure this out, and it doesn't matter the accuracy of everything else. And we did some field work where at the end you're like, oh, we had stylus wear. So now you start figuring out what exactly is the implication, what does it affect, and how much. There was one stylus shape that was a lot more prone to error. So there's been times we couldn't produce ultimate strength because that stylus was just way off. They were asking us primarily for yield strength, so we're still able to do that. But once we figured out the issue, we still went to about 2 more iterations of our surface preparation over the past 18 months, and it's a lot smoother because you know what to avoid in the process. It was painful because it was essentially a month before the blind test is where we had the problem, because we knew we were going to test 50 pipes at different locations, so it was a tremendous amount of work. It was going to be 4 weeks of work, so we had to upgrade our surface preparation. We figured out the issue, sort of verified that the fix was working, and then right away we were in testing mode with it. We had 3 days before the day we wrote the last procedure, tested it out, and we were doing the program. Now, after the program, we were waiting to deliver the results because we needed to rerun all our pipes. We realized we had an issue, so a lot of our own data on our own pipes was off. So, a lot of iterations. I hope that gives you a flavor. And I brought this. So, a bolted connection, and the bolts are represented by springs. Looks very simple, but I've struggled myself, and then I've struggled with a lot of engineers explaining the importance of preloading a bolted connection. So let's say I try to swing it here. Nothing happens really until, I lose contact. So the importance of preloading on a bolted connection is you want the 2 flanges to stay in contact, because if you start losing contact, now these springs are going to fatigue heavily. For the same amount of variation in load, if you're still touching the flange, nothing happens. But once you start losing, this is what happens. So it's important for telephone posts. But also a lot, this was a piece for fracking in oil and gas, and there's a lot of cycles. They throw some explosive down there, and then it moves all the piping. So you need to be absolutely certain that you've loaded these bolts. It looks crazy. You load them to 80% of their yield strength. That's a typical high strength bolted connection. So you use these bolts only once. You damage the treads in the process. And it's not to make sure that they don't get loose. That's not the goal. The goal is to make sure that your flange always touch and you're never going to get that cycle load. So at 80%, let's say you get a 5% load variation, but you will get a 20% load variation if it wasn't touching. So we could go through it, and you probably will believe it, but you won't remember as much as if you actually try it. And with this we had a stick coming because it's a side load that causes most of the issue, a twisting. And yeah, you twist, nothing happens. Oh, it moves. I mean, you can also leak, so that's also bad. But let's just assume there's no leak for now, and it's got a nice gasket, which is a lot of times is the case. So value of putting it together. This was for a consulting job, so client was paying, but sometimes I wish our team would do a little bit more of this, because yes, it's a little bit of effort. Some of the stuff was just cut in layers with a little, I don't know exactly what it is, but you have your own little tool that cuts parts out of the plastic, the wood, and then you stack it, you glue it together. If it's something that's important, we do it with oil and DTT. We made so much out of foam, just looking at the shapes and getting a sense for what we're looking at. So it's more powerful than the computer, in my opinion. What do you think? What do you need to do for prototyping?
Iterate.
Yeah, a lot. Just like learning to ride a bicycle or your skateboard, right? First time you tried it. There was a few things you needed to figure out, right? The first one was balance, right? Then eventually you learn to stop and things like that, turn. All right, well, thank you very much.